Place a book flat on a weighing scale and you'll measure its weight. Now stand the book upright on the scale and you measure the same weight. Also, if you stand the book up on one of its corners. Now do the same with the book on your hand, and in the upright positions it seems to be pressing harder. And on a corner, really harder. You feel more than its weight. What you feel is a greater pressure. We distinguish between force and pressure. Pressure is defined as force per area. Place a book on a table and its pressure against the table is its weight divided by its area of contact. If you place two identical books on the table, one atop the other, the combined weight is doubled and the pressure is also doubled. More force is exerted on the same area. Stack more books atop the two and weight and pressure further increase. The pressure is due to the weight of the stacked books. And so it is with liquid pressure. Just as pressure at the bottom of a stack of books increases with more books, the pressure at the bottom of the tank of water, where the red line is, increases with depth of water. The pressure at the bottom of a tank of water is due to the weight of water above, plus the weight of the air above it, a point that I'll come back to in a moment. The water pressure is directly proportional to the depth of the water. We express depth with the letter H for height of water. We're considering water here, but the physics applies to any liquid. Pressure is proportional to depth. Liquid pressure also depends on the weight density of liquid, that is, the newtons of weight per cubic meter, which we express by the Greek letter rho. We know that mercury has a greater density than water, so there's more pressure at the bottom of a flask of mercury than in the same flask filled with water. So we say, pressure is proportional to density. Putting these ideas together, we say that pressure in a liquid equals weight density times depth. More specifically, the depth beneath the water surface. You can check the units here. If rho is in newtons per cubic meter and h is in meters, the product, rho h, will be in newtons per square meter, which is pressure. If we express density as mass per volume instead of weight per volume, then the equation takes the form pressure equals rho gh, where rho is kilograms per volume, which when multiplied by g, the acceleration due to gravity, gives weight density newtons per volume. In this lesson, our liquid will be common water for simplicity. At twice a given depth, water pressure is twice as much. At 3 times the depth, water pressure is 3 times as much, and so forth. Now back to the atmosphere. We live in an ocean of air, and just as pressure at the bottom of a body of water is due to the weight of water above, atmospheric pressure is due to the weight of air above a given point in the atmosphere. So total pressure equals water pressure plus atmospheric pressure. We'll treat atmospheric pressure in a future lesson, and for now just acknowledge that the pressure at a point beneath the surface of water is due to the weight of water above that point plus the weight of the atmosphere. Then we're speaking of total pressure, the sum of both air and water pressures. In this lesson, we'll concern ourselves only with water pressure without regard to the normally ever-present atmospheric pressure. Let's keep it simple. What's interesting is that pressure does not depend upon the amount of liquid present. Volume is not the important factor. Depth is. The average water pressure that acts against a dam depends on the average depth of the water and not on the volume of water held back by the dam. As an example, a large shallow lake with a depth of 3 meters exerts only half the average pressure against a dam that a 6-meter deep, small, deep pond exerts. Consider this set of vases connected at the bottoms and filled with water. These are called Pascal vases and are popular in classroom demonstrations. Although the volumes of water in each vase differ, the depth of water is the same in each. That means the pressure at the bottom of each vase is the same. A pet goldfish at the bottom of any of the vases experiences the same water pressure. Pressure depends upon depth, not volume. Hence, we say that water seeks its own level. Consider water towers in common suburban areas. The water has to be pumped up into the elevated tower, but once it is there, no pumps are needed to provide water pressure to homes connected to the water supply. Gravity supplies a constant and reliable pressure. More yum. Think about swimming into a cave beneath the surface of water. Here we see that there's an airspace in the top part of the cave. Guess what the air pressure is at the air-water interface? That's right. It's the same as the pressure anywhere else in the water at that depth below the free surface of water. There is no pressure change from one place to another horizontally, which is to say, there's no pressure gradient in the horizontal direction. The pressure change, or pressure gradient, is all in the vertical direction. So we see that pressure in water depends upon the depth below the outer free surface. Is this yum? I didn't give any illustrations of the density part of liquid pressure. I'll do that now with this concluding question. Suppose you dunk your head a certain distance into a barrel full of water. You'll feel water pressure against your ears. How would this pressure compare if you dunked your head the same distance into a barrel full of salt water? Think about that, and take into account that salt water is denser than fresh water. Until next time, good energy.